Welcome back. Okay, except for human-created things such as buildings, there's very few straight lines in nature. Examples would be coastlines, mountain ranges, hiking trails. Those things could be represented based on straight lines using something known as fractals. I have a diagonal line running from 0, 0 to 1, 1. If I apply fractals to it, or a fractal algorithm, I get a basic random configuration. It's really just a polyline that represents variation in that path. And the longer I do this, because it's based on random numbers, I'll get different configurations. Now you could take something like a coastline represented by a straight line, apply a fractal algorithm to that line or set of lines, and create something that is pretty realistic. Now I'm going to go to a diagram and start explaining how this works. Okay, the end goal is to create a polyline that is a randomized representation of the original line. Now in this case, we have a line AB, which is basically the same as the one that I had in the previous demo. It's just at a 45-degree angle. I want to do recursion, and this is the first pass down the recursion in this particular example. I find a midpoint of the original line called M, and I can calculate the position of M simply by taking the average of the x components of A and B and the average of the y components. Now I want to take a displacement. I'll call it T. And if the displacement is this direction, I'll end up with a point called Q. Okay. Now that gives me two additional lines. It gives me an A to Q and a Q to B. And then I want to perform a recursion for this line and that line, and continue on to the point where I get small enough that there's a limit. It doesn't really matter, because if you can't draw a line a certain length, you might as well just stop. Plus you have to stop recursion at some point. The T, displacement, is based on a random number. And you want that random number to have a mean of 0, because you want to be able to have this either on either direction of the two lines along the T displacement. Now you can calculate Q, because you need to know that for the two recursions, based on T times the difference, let's take for X, the difference between the Y components. So in other words, if there is no difference in the Y component between A and B, in other words, if it was laying on the axis, then this would be 0, and you wouldn't have any change in the X component. The Q would be the same as M. Okay, now that's an example of what's happening here. So in other words, the change in Y has the effect on QX, and in QY it's a similar situation. You simply add the displacement times BX minus AX. In other words, how much was the change along the x-axis? Okay, now what I'm going to do at this point, you may have to just stop and back up and take a look at this diagram and go through the calculations yourself once again. I'm going to go over the code now. Okay, the Fractal Code has been added to the line structure. There's a function which kicks off the recursion, and then there's the recursion function itself. Now, what I did not explain to you is what has to happen to the displacement t. As you get deeper down in the recursion, the lines get shorter, so the displacement has to be decreased. And there's two parameters. There's a standard deviation. In other words, what is the deviation of the random number that's generated? And there's a scaling factor that is used to scale that deviation as you go deeper. And you'll see that there's two parameters. There's standard deviation and there's something referred to as scale. Now, we use, or I used for the demonstration, a deviation of 0.1 and a scale of 0.8. If you change that, you're going to get different types of fractals. They're going to have somewhat different characteristics. Now, in terms of the recursive function, the first thing that has to happen is I have to calculate the length of the line because I need a stopping condition. I use the Swift power function, which enables you to raise something to a power. I square the x and y components. If you raise something to the power of 0.5, that's the square root. Now I have a constant which defines the shortest length, and that's based on not wanting to recurse too deep and still get a reasonable visual effect. So if the length is less than the min length, then I simply just add the current line to the lines array. And this is where the recursion stops. Else, we're down in recursion. We need the displacement. And the way I get that is I call a function called random on the double type. And I want something that varies between the negative of the deviation and the positive of the deviation. Now I want to calculate the point Q. And we've seen this in the previous diagram. I'm effectively creating an M, and I'm figuring out what the displacement from M is for that point Q. At that point, I want to change the deviation that's used, and I want to multiply it times the scaling factor. And then I want to call this function, the recursion, twice, each time for the new lines, A to Q and then Q to B. That's it.